Good morning, mathematicians. Welcome. Hope you're doing well. I know I lied. Ooh, look at that. 6K. Wow. Thanks everyone for subscribing. That's sweet. Oh, I didn't mean to add myself to the queue. Being Saturday, I assume there'll be a lot of, and being that I started later, I assume there'll be a lot of questions in chat today, which is good. It'll keep me busy. Whenever people show up. Oh yeah, isn't there's something new? I haven't even looked. I'm a bad mathematician. I haven't even looked into. There's some exciting new news surrounding fast matrix multiplication, right? Oh. Hello. Good morning. At least I think that was supposed to be a hello. or is that a bot, like, spamming my chat? You're watching my discussion about Voevodsky the other day, and it reminded you of Edward Frankel's book about the Langlands program, his autobiography with Langlands. Wait, with Langlands? You mean his autobiography with the Langlands program in it? Not. I have read it. Yeah. Yeah. You don't mean Langlands is in the book as well, autobiographically. You're not a bot. But then why a sad face? A sad face because I thought maybe you were a bot? Oh, 27. Oh, that's brilliant, actually. That is brilliant. I see now. I see. Okay. After Rod pointed out the 2.71. Yay. Yeah, that was great. That's real good. That's real good. That's real good. This is a fascinating question. What is the difference between being equal, and being isomorphic? Amazing question. A deep question. What does it mean for two things to be the same? Okay, so the regulars will be sick of me talking about Ewodi's paper. But you know, let me show you another interesting paper along kind of similar lines. Univalence moment. Yeah, absolute univalent moment. Is this 2025? I guess this is maybe an updated version of the same one. So it's called Mathematical Reasoning on the Computer. But even if you don't care that much about proof assistance, I think there's some interesting things in here. Oh wait, am I confusing this with another paper maybe? No, I am confusing this with another paper. This isn't the one I wanted. Is this the one I wanted? Yeah, this is the one I wanted. What's it called? Grothendieck's use of equality. Yeah. Discuss how the concept of equality is used in mathematics. It's really interesting because assertion 3 is we like our canonical isomorphisms, but can anyone define a canonical isomorphism? Yeah. I don't think there's any definition that takes care of all of the uses of canonical. And even if we had one, um, yeah, I mean it's a messy thing. So I recommend reading this. If it smells canonical, yeah, yeah. But that's so I do think even if you don't care about proof assistance, there's interesting things to discuss here, even though he will bring up proof assistance. And one thing I will say is, when it comes time to prove something in a proof assistant, there's no hiding behind. There's no hiding. You got to supply the terms. You got to supply the proof. So there's no smell test for canonicity, which is maybe what spurred this paper. Yeah. What is this article? This article is Growth and Deek's Use of Equality by Kevin Buzzard. Can find it on Archive. Just Google it. How do we know that distributions, intuition, improving? What do I want to talk about today? How strong are successful Ph.D. students in math? Oh, interesting. How is it possible to remember more than 100 proofs for academic year? I mean, that's actually not that crazy. Depends on the length of the proof. And I don't know. Like, if you take a class in something and you use that same theorem and prove it a couple times, like, I don't know. You'll be able to, like, eventually recreate that proof, you know what I mean? Yeah, interesting. Let's take a look. Let's see. Fundamental theorem of calculus. Really? Well, it depends on what... to be able to prove all of these? Well, to what level are we going? Are we doing, like, the Riemann integral? Are we doing the Lebesgue integral? Like, to what level of rigor? I've always thought of canonical as hinting at some sort of hidden naturality underneath, even if it's difficult to make an explicit natural transformation. Yeah, okay, but there's problems with this. So definitely go read this article. But yeah, and lots of people say that, but there's two problems. Problem number one is that, well, people say this. It doesn't always get used this way in the literature. And moreover, it is difficult because, as you say, even if it's difficult to make explicit as a natural transformation, well, if it's difficult to make explicit as a natural transformation, then that's all the more reason you need to back up your claim and actually show the details. But it seems the more difficult it is to actually show that there's a natural transformation hiding somewhere, the less likely people are to do it. But also, for example, there's like geometric Frobenius and arithmetic Frobenius, and Kevin Buzzard brings this up. And there's like There's no naturality thing going on here. Here they just mean canon in more of the colloquial sense that this is the choice that we all make. Except mathematicians are split depending on what field you're working in. So that's problem number one. And problem number two is, well, if we have some sort of like canonical identification, right? Being some sort of natural transformation, well, there could be more than one natural transformation, right? So, there is a canonical, right? And then the way that we normally use canonical isomorphisms is we say that we're always going to identify, say, like objects. This is the value of some functor. Identify, objects along this morphism. But then what if, in general, you should expect there to be a bunch of natural transformations between functors. So what does it mean? Like, there's this psychological division. Like, people say, oh, yeah, well, it means that there's an underlying natural transformation. Yeah, but then in the way that we treat these things is we're automatically identifying things that are related by this isomorphism. There's going to be more than one isomorphism, though, in general. So how do you pick that? Good morning. Just bought a new laptop. Hell yeah. And selling all the math crap on it. Hell yeah. That's a good way to spend a Saturday morning. Are you evil for using that FR for both geometric and arithmetic? Well, I don't know. As long as you're clear about when you're using what when. If you're not clear about it, then yes, you're evil, and I'm gonna have to hunt you down. You'd argue that calling a choice of Frobenius canonical is just wrong. Yes, I agree. Especially in Galois theory. Yes. I don't think this is the only instance in math, but yeah. The article sounds interesting, although you don't really have much background in number theory. Yeah, I don't think it's so bad. Even if you don't have the background. Oh, that's not where I meant to go. Like, he does do some examples. So there's an example here where he talks about localization of rings. He says some words about algebraic geometry, but he's mostly just talking about localization of rings. Like, the first part is like, he's just talking about sets, and the universal property of sets. So, like, yeah, not a big deal. And then localization. So I don't know if you're unfamiliar with like the concept of localization, but I don't know if you have some basic algebra, it shouldn't be too bad to at least get the idea of what he's trying to say. And yeah, first isomorphism theorem. Okay, here maybe towards the end of the article, there's this would be something a little more difficult to understand if you haven't seen these ideas before, like Galois cohomology or whatever. But I think it's still readable enough. Like okay, it's just this one short. It's this one page in it where he talks about it, and I think given the rest of the things that he talks about, even though the technical words themselves may not make sense, learning basic AG but nowhere near research level, then I think this paper is totally readable for you. There'll probably be some things that go over your head, but that's reading math for you. What's my favorite type of localization of categories? I just noticed the other day there's surprisingly many. Interesting. Let me get to that in a second. But Ethan says, apologies if you've discussed this already, but there's a precise sense in which natural means no arbitrary choices. Is there a precise, rigorous way to formulate that purely mathematically? in a way that you could say prove a certain map is canonical, like formalize this in a proof assistant and then prove formally that a map is canonical. I'm not sure that that's the case. You're aware of the dual space example. You're wondering more generally. Is there? No. So no. I think no. I mean, there is this vague sense, right? So there's a general principle. There is a general principle. Is it It's this principle, right? Yeah. There is a general principle that says canonical or choice free, or whenever someone says natural in a colloquial sense, usually these hint at the existence of a natural transformation of functors. Like you said, you're aware of the double dual thing for finite dimensional vector spaces. But this general principle is not rigorous. That's what this whole article is about. I encourage you to go read this article as well. It's there isn't a well-formed way of proving this or showing this. Like, it just seems to generally be the case. Well, I mean, it could be possible that one day someone will come up with the right way to formulate a very precise and rigorous definition of canonical isomorphism. But until then, this is all we have. To answer the question, well, I only know I've only ever learned one localization of categories. That's the or localization, which is maybe inelegant. I know. Probably the better way to do things is to go to some infinity category and localize there, I'm sure. But I don't know that. I just know, like, or localization. Like, you take your category, you take your set of morphisms that you want to invert, and you take your category and you turn it into a digraph, and then you formally invert the arrows in W, and then you turn it back into a localized, turn it back into a category. And then you do all sort of fancy gymnastics for how you define your morphisms. That's all I know. Do I think it's pointless to learn about schemes if you don't care about number theory? No, absolutely not. Absolutely not. I mean, modern algebraic geometry is all about schemes. So if you care about algebraic geometry, then definitely I think it's worth learning schemes. You learn some classical algebraic geometry, say from Hartshorne. You don't know if you should continue Hartshorne or learn the complex analytic picture. Yeah, I don't know. That's entirely up to you. I think it's helpful to have, the complex analytic picture. And I think there's cool things going on there with the connection between complex algebraic varieties and complex manifolds. But yeah, I guess it just comes down to what direction you want to go in. I mean, if you made it through chapter 1 of Hartshorne, then arguably maybe you don't need the intuition coming from differential geometry, because you're able to make it through there. Yeah, I don't know. Hard to say. There's another localization used in equivariant cohomology, not related, but useful in enumerative geometry. Oh, it's a localization of categories. Or what kind of localization is it? Been a while since you joined the stream. Nice haircut. Well, thanks. Thanks. I was saying before when I got it that it's not my favorite, but I'm settling into it. Yeah. Okay. I guess we gotta yap about some math or something. Oh, there probably won't be a live stream tomorrow. By the way, I'm going on a hike, and we're leaving early, so I don't think I'll really have time to stream in the morning, and we're not getting back till fairly late. So it could be an idea to do like an evening stream, but I don't think I'll have it in me. Makes you wonder if you learn things too abstractly, then you lose a lot of the intuition the old masters had with doing everything analytically. Yeah, I mean it's a balance to strike. I don't know, hard to say. I feel that way too. But then I don't know. I feel like there's I don't know. I can imagine like a younger generation picking up the newer, flashier, abstract tools, and then forgetting the previous intuition. You know, like you could imagine there's a sense, like there's a part of me that believes that that old intuition that originally inspired the definitions are what's really useful. Is really useful for you to work with those tools, but then one could imagine that maybe the old definitions and ways of thinking are also holding you back in a sense, right? So, you know, like in the same way every generation, I don't know, like bests the previous generation. So I don't there's people growing up on infinity categories now, and it'll just be a natural thing to them, and the dinosaurs will be left in the dust. Such as myself, I suppose. A Tia bot localization. Never heard on the stream. Am I from and in Canada? I am indeed. I am about. I am somewhere about the Canadian region. A Tia bot localization. I guess we'll just look at this. Localization and equivariant cohomology. Interesting. Topological group, yeah. The Borel equivariant cohomology of X for a G action is defined as a cohomology of the homotopy quotient. We denote the space by the diagonal. You take EG and X and you quotient out by the diagonal action. I see. Hey, you still have a problem with the bib part while documenting your research paper in Overleaf. Can I help? Maybe it is probably going to be very difficult for me to help because like without seeing your screen and stuff. Yeah, I don't know. It might just be better to go to like Overflow or Stack Exchange. I mean, I don't think there's an overleaf overflow. That'd be funny. Real advanced overleaf problems. Well, documenting. Yeah. I don't know. You can try and describe the problem, but it's going to be hard to troubleshoot it on live stream. I can show you like a bibliography that I use. Maybe what paper do I want to show you? I guess I can go here. Oh, wait, that's not where I meant to go. Yeah, speaking of dinosaurs, here's an embarrassing moment. I'm not using a bib manager. I literally just have a whole list of things I copy paste in. So I'll show you. This is the I'll show you the bib command that I do. Yeah. I just do bib div bib lists, and it seems to work fine with me. For example, you can compute the 27 lines on a cubic surface using this in 4 lines. Really? Wow. Wow. How? Is there is there a source that does that, has that 4-line proof? That would be awesome. Can you really though? Because I mean, I feel like what we're looking at here is this is all homotopy level type stuff. I mean, so I'm sure you could do it in 4 steps, but then like if we're talking about the 27 lines on a cubic surface, that probably means we're going to algebraic geometry land. So that means we need to think of BG as a stack. It's in this paper that I'm looking at right now. What the hell? No way. For a more involved and interesting application, let us show how one can use the tool of equivariant integration to recover the classical enumerative result that there are 27 straight lines on a cubic surface. Whoa. Okay, so I guess we are using like the analytic topology to do it anyways. I'm just thinking about polynomials. The actual number can be computed by the following integral of the Chern class. The calculation scheme. So this is like a more classical proof, right? That's not the alleged 4-line one. Wait, no, that's the proof. This didn't look like 4 lines. And wait, where exactly did the equivariant cohomology even appear? Very unclear to me. Super intriguing. Got to spend the rest of your day on this now. Yeah, I'm definitely going to look at this later. Especially since in my research there's some symplectic geometry and moment map stuff. So I'll probably have a look at this. I'll probably have a look at this. Yeah. Anywho, what else is there to say? What else is there to yap about? Oh, we didn't finish going through this list. Things to prove. What the hell? You have to compute equivariant weights under a certain T action. Weights in what sense? Like like weight in what sense of the word? Oh, is it from this? I see. Like, because you can interpret weights in like the Lie algebra world in terms of some Flag variety cohomology stuff. Right. I see. So it gets used up there. Okay, I'm definitely gonna take a closer look at this after, for sure. I do want to go back to this list of theorems that I'm supposed to know, though. Cauchy-Lipschitz. I don't even know it. I know I'm supposed to know it. I don't even know it. Density of Q and R. Yeah. Something about convergence, divergence. Bolzano-Weierstrass. Yeah. This all seems very analysis bias first, but we'll see. We'll see as this list goes on if there's a balancing out of algebra terms. Sequential characterization of continuity. Yeah, axiom of choice is in there in one of those directions. Okay, it does look like it's balancing out a little bit. We've got Gauss's theorem. What is that? Do you have any idea how little that narrows it down? Am I supposed to know every theorem called Gauss's theorem? That's unlikely. Characterization of subgroups. Yeah. Heine? I have no idea what Heine's theorem is. Heine-Borel theorem, maybe? I don't know. Lagrange interpolation. Really? I mean, it's a great theorem. I love it, but I don't know. Should you? I would not. I don't know if I would put that on my list of like things you need to know. Good morning, Julie. Hello. Yeah. I don't know. This is a weird list. Batman Beyond reference? Wait, where? Batman Beyond reference? Huh? Or they say something in here that's a Batman Beyond reference? I don't know where it is. Okay. What's some math to yap about? What is some math to yap about? I don't even know. My brain is empty. It's been a long week. It's been a very long week. Why don't we talk about the Moore graphs? Because I'm obsessed with them. So let me let you guys in on maybe a secret. Oh, how little it narrows it down. Ah, yes. Is that Batman Beyond? Is that the series? Yeah, I don't know. I just know the meme. So recall my favorite problem. I made a short about him. Oh yeah, yesterday I promised you guys a short, and then I didn't make one because you know what? I didn't feel like it. We want a k-regular graph with k squared plus 1 vertices. And it has to have length 2 and girth 5. Those are things. And if such a thing exists, k has to be one of these numbers. And we know that it exists and is unique up to isomorphism for these. And we have no idea if the case for 57 exists or not. Did I already talk about this on stream? I don't know. No, I know I did, but the thing I'm about to say, I don't know if I did. But I've been thinking a lot about... oh, yes, because I think I gave this as homework. I think I gave counting the cycles as homework to everyone. And you guys didn't do it, so shame on everyone. Unless you weren't a fan at that point in time and following the channel yet. In that case, shame on you anyways. For not being here sooner. So k equals 2 is the 5 cycle. K equals 3 is the Peterson graph. Okay, so now here's the beginning of some mysteries that I don't understand. Let's count the number of 5 cycles. So take an arbitrary vertex. We're going to count the number of 5 cycles containing this vertex. Well, we have k choices for the first, because it's k regular. So we have k choices for the first edge in our 5 cycle. We then have k minus 1 choices for the next edge in our 5 cycle. And now there's no edges between these because it has girth 5. So there's definitely no triangles in the graph. And so there'll be no common neighbors between this vertex and the first two. So we're totally free to make another k minus 1 choices here. Better silence the group chats. Okay. And then so what do you have? K minus 1 squared. Right. And then now well, this is a strongly regular graph, by the way. So you can actually prove this from these conditions. But strongly regular graph, meaning that every pair of non-adjacent vertices has exactly one neighbor in common. So why is that true? For example, vertex 1 and vertex, maybe I should call it 4 here. So there can't be an edge between them because then we'd have a 4 cycle. But also the length has to be 2. Right, so we can't transverse the path this way because that's a distance 3 path. So there has to exist some vertex here, right? That connects them, and there can't be more than one because if there was more than one, right, we would have a 4 cycle. So that's why it's strongly regular. So okay, that's our count, except this last edge that got forced, that could have been one of the k choices that we made to begin with. So we actually have to divide by 2 to get the accurate count. So there are, around every vertex, there are this many 5 cycles. So in total, in the graph, the total number of 5 cycles is just, well, we multiply by the number of vertices, and of course each vertex appears in 5 cycles. Or sorry, no. That's not true. Uh, that's not true. But this any given 5 cycle will be counted exactly 5 times, once for each of these vertices, is what I meant to say. So this is our total number. Have I said all of this before? I feel like maybe I even said all of this before. I don't know. Now here's what's interesting. Here's where things start to get mysterious a little bit for me. So it turns out that if you look at the span of, how do I say this? Okay, if you look at the power set of the edge set of a graph, this is an F2 vector space under symmetric difference. And the span of Eulerian subgraphs, or the collection of Eulerian subgraphs, which is to say the span of all the cycles in here, this forms. You recall me talking about this, but not so knowledgeable in graph theory. Well, then good. Then you get you're getting re-educated on it. So it's the number of edges. The dimension of cycle space will be the number of edges minus the number of vertices plus 1. So the number of edges, this is a regular graph, so it will be the number of vertices multiplied by the regularity divided by 2 minus the number of vertices plus 1. And lo and behold, what does this work out to be? It works out to be this number here. And that's not maybe so surprising, because if we draw sort of like a rooted tree diagram of this graph at any vertex, right? It's diameter 2, so it'll kind of look like this. There's 57 neighbors here, and each of those have 57 neighbors. Now, if you look at the 5-cycle made by simply all the missing edges here, all the missing edges are just edges between vertices of this form. And if you do some basic math, you can count that there's exactly this many of them. And because, basically each one of them has their own unique edge, you can see that they'll be linearly independent with respect to the symmetric difference operator. So that's not so crazy. What is crazy to me is that by, and I don't have a proof of this, by inspection, for k equals 2, 3, and 7, but I'd like to find the general proof that also works for 57. By inspection, there appears to be k times k minus 1 squared, so exactly equal to the basis elements, ways of decomposing this into disjoint 5 cycles. So what do I mean by this? So let's take the Peterson graph. How do we decompose it into pairwise vertex disjoint 5 cycles? Well, here's one way. You just forget all the edges connecting the middle pieces. And then here's another way, is you look at these, you drop all the edges except for the ones making it these 5 cycles, and then of course this one you get 5 of these, because you basically just rotate this whole picture around the graph. So for a total of 6 ways of decomposing it into pairwise disjoint 5 cycles. Yeah. For no reason, this reminds you of discrete automorphism groups. Well, a graph is a discrete structure. I don't know what you mean by a discrete automorphism group, but its automorphism group is a discrete group. That's a finite group, so I guess that makes sense. Um, and yeah, so but why is a question, and I mean, you can just verify this through like raw computation for the graphs that are known to exist. But here's a question, like why uh why is it that the rank of cycle space is the number of 5-cycle decompositions? Fm equals Fn, where f is a function from x to x. Show that f is 1 to 1 if and only if f is onto. You're asking me to prove this? Maybe. Can you construct all number of graphs with a certain number of automorphisms? I think that's hard. I think that's extremely hard in general. Like, you can prove that for every finite group there's a graph with that as an automorphism, as its automorphism, with a given group as its automorphism group. But yeah, I don't know. Hang on, let me write down this question. So hang on, just for some m and n, greater than 1, I'm guessing. And then we need to prove that f is 1 to 1 if and only if f is onto. Okay. Is there a theorem? Yeah, if you just yeah, there is a theorem, but it's very like it doesn't work in any sort of systematic way, right? It doesn't really work in, m has to be bigger than n. M has to be strictly bigger than n. But the theorem isn't systematic in any way. Yeah, I don't know. I feel like it would probably be hopeless in general. Like, probably you could classify those graphs that have Z mod 2. Actually, no, that's not even true. Like, I feel like it's probably hopeless because, like, look at this graph. Like that Nickelback song. Look at this graph. Look at this thing. This has trivial automorphism group. I don't know what else to say. Arcturus, well, you're reading it, but are you understanding it? We've had this discussion a lot of times before, and one thing I wanted to say is, how do you know? So you're claiming that you understand these things, but how do you know that you understand them, right? Because it could be easy to read something and to think you understand, but then, for example, you take a test in class and you don't do as well on the test as you think you did. Happens to everyone. So how do you know that you're understanding the material? Well, you can engage in discussion with peers or superiors. Of course, you can take classes. So you say you're reading Noe Kirsch's number theory. Well, how do you know you've understood it? Are you taking a class? Have you taken other classes in that before? Have you consulted other mathematicians to get their opinion on whether or not you're doing things correctly? Because Previously, you did send me some material, as I asked you, to try and prove a very basic statement in set theory. You failed to do so, and then you said mean and nasty things to me and called me a total idiot. So I don't know why I'm still trying, but I want to pull you back from the edge of total crackpottery, and I really hope, I would suggest that you, again, go slowly and carefully through a book like Polya's How to Prove It and learn how to actually prove things rigorously. It very well could be. Maybe you actually do understand a bunch of things that Neukirch is talking about, but it is clear at this point in time that you do not have the ability to communicate that clearly to other mathematicians. And if your future work is going to be considered, if you want it to be taken serious by the mathematics community, you're going to need to be able to communicate that to other established mathematicians in a way that they can understand. So I highly recommend that you work on that. Okay. Although you're not sure if it matters if m is less than n, just switch sides. No, yeah, I mean, m and n are just arbitrary integers, right? So it doesn't really matter which one you say is the bigger one. So yeah, where are you stuck in the proof? Let's just take a low level. Let's just start plugging it. So suppose f is injective. And we want to prove that f is onto. So let's just begin with the most basic way of approaching this. Let y be an x. So you can show f is 1-to-1 implies onto. Okay. The other way you're kind of stuck. So how did you do the forward direction? Let's maybe start there. I'll answer some other questions while you type that up. For every n greater than 1, is there a graph such that the automorphism group? Yes, to Ken's question. I mean, in fact, a stronger statement is true. For every graph, for every, yes. The statement's even stronger than that, though, right? It's for every group gamma there exists, for every finite group, there exists a simple, connected, undirected graph G such that the automorphism group of G is gamma. So significantly stronger statement is true. You don't like Neukirch. Do I have any alternative with almost the same content? No, certainly. Well, not in terms of like the scope and amount of things that Neukirch covers. You could try Marcus, number fields by Marcus. Try number fields by Marcus. Or you could try Milne. Milne has books on algebraic number theory. Actually, yeah, Milne would have a lot of stuff in it. Those are other two that are worth looking at. So you can show. Okay, maybe I should just do this. Are you still typing? Maybe they're still typing. But your reasoning is kind of vague when say. Sorry, I'm not sure I understand. Let's try and go your first comment didn't go up. Okay, let's just try and go through the first part of the proof. So f is injective, and we're trying to show that f is onto. We somehow need to use this property. Well, y is in x, so what can we say? So then, what do we say? Well, somehow we'll need to use this property. So fm, fn is y, but that means what? I mean, what do we get? We get f m minus n fn y is equal to fn y, or maybe I want the n on the outside. That makes more sense. Yeah. So we have fn of fm minus n y equals fn y, but f is injective, right? So that would imply that fm minus n y is equal to fy. Wait, but where does that get us? M is n plus k. Yeah. Let me write this down here. Right. So m is n plus k, and we have fn fk of x is equal to fn x. So the range of fk is x. Wait a second. Oh, right. Yeah, so sorry. That implies that fkx is x. Then you say the range, I see. Right, so it is surjective. I see, I understand. Do I think you can't prove because you wanted to create your own proof method? Nope, that's totally fine. You can create your own proof method, but it does need to be logically valid. You do know the art of proofs. Again, how do you know? How do you know, right? Because, how can you be sure that you know the art of proofs? Do you have a degree, for example? You don't necessarily need a degree. You can learn how to prove things without a degree, but you need some way to be sure, some sort of test, some sort of assurance, right? So a good way to have that is to get a good grade on an exam. And so like how can, and also how can I be sure? Like, you can make these claims, that's fine, you might be right. But how am I supposed to believe that? There's if you have some credentials that you could provide, that would be worthwhile, or if you could provide a logically valid proof, but neither of these things have appeared. The reason your material is so janky because your proofs don't rely on standard methods, well, but they still need to be readable to other mathematicians, right? No, that I don't think that's the issue. Just using the fact that you use contradiction. Again, yeah, I don't know what to say. I don't know what to say. I hope that you'll stop going down this path that you're on, and you'll take mathematics seriously. So how do we go the other way around? Right, so we get to here, and Right. So we used the injectivity here to get this implication. How do we get the converse implication? Oh man, I'm so far out of coffee. How do we get the inverse implication? So come back to this statement, and now we suppose that f is surjective. We could also try starting from some supposition that fx is equal to fy, right, for some x and y, and try and show that x and y are both equal. Well, again, we could get to some statement of this form. Well, we know all of these things must be equal. Hello, Vihar. Yeah, to be honest, I'm kind of ready to end the stream, but I don't want to leave this question unanswered. And there's so many other things here in chat. Yeah. Let's see. What are we trying to prove? We're trying to prove it's injective, right? Well, I guess. Never mind. You'll check back tomorrow. Yeah, maybe I'll have an answer for you then. Sorry about that. F is surjective. It's still kind of bugging me. Let me just quickly look at the chat here, see what other questions we had. General question, how do I approach research problems in a structured way? I don't approach them in a structured way. Usually I have too many different ideas and struggle to make meaningful progress. Yeah, I don't know. You just got to bite down somewhere, and yeah. I also take a chaotic breadth first search approach. Yeah. Reading Marcus number fields now, is there further motivation for why we care about the discriminant? It just seems algebraically natural since you get bilinear pairing from trace, but I have no further intuition. Well, I mean, it's kind of some grand generalization of the discriminant of a polynomial, right? We were talking about discriminants recently, yeah. All right, then here's a deal if you like. So tell me you're a mathematician of expertise. I'm not sure what your question is. Discriminant is very useful for determining Galois group of polynomials. True. Yes, that's also true. Like there's a, like you can completely classify like Galois groups of cubic polynomials based on whether the discriminant has a square or not, has a square divisor or not. Actually, that's a really fun problem. Maybe I should talk about it. Okay. I still kind of want to prove this though. Suppose it's surjective. These things are equal. I mean, somehow we need to use the surjectivity. So we've got all of these equalities here. Yeah, I don't know. I mean, I'm tempted to do an induction. Like, what if we knew this? What if we knew this? For example, what if we took n to be equal to 1? Yes, we're trying to show surjective implies injective. Yeah. Right, so if we knew this, then what would we have? Well, our basic assumption would give us this. I mean, could also maybe write things like this. Yeah, I mean, we'd have to do some sort of like double induction or something. Some sort of double induction, yeah. Right. I mean, but I'm imagining just letting n be equal to 1 and letting m be arbitrary. Then what do we have here? These have to be equal. Think about the definition of epi-mono. Oh, right. Yeah, I see. Right. Right. Epi means so if you can get some power of f is identity. Right. So on the one hand, let's do it this way. Right. So if we go f m minus 1 f, or even let's go back to f n plus k equals fn. Right. Then we've got f. Right. So epimorphism, which is to say onto, means right cancelable. Then wait, is it we cancel it when it's on the right? Okay, I don't remember. But the point is either way, one of the conditions onto will give you that this onto or injective implies this, and then the other condition will apply it on the left instead of the right. So both conditions give you this, right? But then that shows you either way. This means that f itself is left or right cancelable, right? Because k minus 1 is at least 1. And then, again, the left-right cancelability is equivalent to injectivity or surjectivity. So we're good. Okay, I'm going to kill the stream there. It's time to go. Time to start my day. Time to do some proofs. So thanks for joining. And may your weekend be filled with beautiful theorems. I will not see you tomorrow. I'm not streaming tomorrow. But I will see you Monday.